All right, welcome to Organic Chemistry. In our previous unit, we looked at conjugation, that is, systems that had alternating double and single bonds. But here we're going to see what happens when you take that conjugated system and you tie the ends up into a loop, so you have a continuous ring of p orbitals that interact around the loop. These systems are called aromatic, or in some cases anti-aromatic, and we'll find out what those mean in a bit. But let's go back a couple hundred years. A new compound was discovered with the formula C6H6, and at that stage we didn't have the modern techniques of determining structure, but based on inferences, people came up with a series of proposals for this new, and it turned out to be interesting, molecule. Huckel tells a story that he fell asleep thinking about this problem, and he had a dream where there was a snake that wrapped around and bit itself on the tail. And when he woke up, he realized that benzene must have a cyclic structure, where you had a loop of single and double bonds. Now, Huckel's original proposal had a little bit of a problem. It was fine for benzene, but let's consider dichlorobenzene. If the structure was just as Huckel had described, there should be four possible isomers. The 1,4 isomer, which we're going to later call para, the 1,3 isomer, which we'll call meta, but there should be two different types of 1,2, or what we'll call ortho, depending on whether there's a double or single bond between the two positions with chlorine. But Huckel came back and said, well, maybe these structures are... I should have said, but as try as they might, they could only find three isomers. They could only find three different compounds that had that formula. So Huckel came back and said, well, maybe these two structures were actually rapidly equilibrating. That is, it was going back and forth so fast that you couldn't actually separate them. So he said there was an equilibrium. Well, that doesn't quite fit the data. There's a number of different things that we could look at that led away from Huckel's original proposal. Now today we would actually explain this not as two structures that go back and forth very rapidly, but instead there's one structure that is an average of those two. That is, there's resonance. If we have these single and double bonds around the ring in resonance, that means the real thing is actually an average, where those are delocalized. Instead of having a single bond or a double, we've got something that has the bond order of 1.5. And if we drew this as sort of delocalized bonds, we said that these two structures are really the same thing, right? They're just two different resonance forms showing different locations for those pi bonds, but they're really the same molecule. Now, this idea of resonance helps explain a lot of the interesting properties of benzene. One of those properties is the structure. Let's contrast a hypothetical localized system, which has no resonance, to a resonance-stabilized pi system. If we had a localized system, double bonds and single bonds are different in length. We expect to see something, and I've exaggerated my picture here for effect, but we would expect to see something with 3 shorter bonds and 3 longer bonds. To put some number in that, butadiene has double bonds of length 1.34 angstroms and a single bond of 1.48 angstroms. So you should expect to see 3 shorter bonds and 3 longer. But benzene itself is an average structure of these two, and it doesn't have shorter and longer bonds. In fact, all 6 bonds turn out to be 1.397 angstroms, which is about halfway between these two. Benzene, this is a X-ray crystal structure, is a perfect hexagon, and it's planar. Here, this picture kind of shows it turned on its edge, so you're looking at it edge on. Another interesting property of benzene is its set of reactions. Benzene does not behave like alkenes. The characteristic reaction of alkenes is addition. So if I took 2-butene and I treat it with AR, I would get an addition product, where I added an electrophile and a nucleophile. If I take benzene under the exact same conditions, no reaction. If I take an alkene and I treat it with Br2, electrophile, nucleophile, where my electrophile is quote-unquote Br+, and my nucleophile is a bromide ion. But if I treat benzene with the exact same conditions, no reaction. So benzene is much less reactive than alkenes. Now you can get it to react. Now, you can get benzene to react, but you have to add in a catalyst. And what you'll find is that when you treat benzene with Br2 and a catalyst, you don't get an addition product at all. Instead, you get a substitution product. In this case, there's a hydrogen implicit here that's been replaced by bromine. And what we'll find when we talk about these reactions in detail further on is that the mechanism here is not the SN1 or SN2 or even the free radical substitution reactions that we've seen previously. Benzene and things like benzene, in addition to being less reactive than alkenes, have their own characteristic reactivity that we'll get into a little bit later. In addition to having interesting structure and interesting reactions, benzene has an interesting energy. Okay, let's look at hydrogenation. We've already seen the hydrogenation of alkenes to make alkanes. So if we took cyclohexene and hydrogenated it, we'd get cyclohexane. And this process would be exothermic by 28.6 kilocalories per mole. What would we expect if we had two double bonds? So 1,4-cyclohexadiene. Well, you might expect, and you'd be right, that'd be downhill by twice as much. And this is almost exactly double. Now, this system is not conjugated, so let's consider a conjugated system. 1,3-cyclohexadiene is hydrogenated exothermically by 5 kilocalories per mole. So it seems like there's an extra 2 kilocalories per mole stabilization of this guy relative to this guy due to conjugation, because going from here to this, they end at the same place, right? So if we're going downhill by 57 versus downhill by 55, that means we started higher for the non-conjugated system than the conjugated system. Okay, let's consider benzene. What would we predict based on what we already know about alkenes and conjugated alkenes? Well, if it's just based on alkenes, one's worth 28.6, two's worth 57.4, we might expect 3 pi bonds to be worth 85.8. That's what we might predict. Now, we might make some adjustments to this, because here, comparing the non-conjugated to the conjugated, we had an extra 2 kilocalories per mole stabilization based on that conjugation. So you might expect to get a little less, maybe as much as 6 less, because this has one place where you've got pi bonds adjacent to each other. This one has 3 places. So, maybe somewhere between 80 and 86. When you go in lab and test this, you find out that the hydrogenation of benzene leads to cyclohexane, and this process is exothermic by 49.8 kilocalories per mole. This is between 30 and 36 kilocalories per mole more stable than you might have predicted based on what you already knew about alkenes and even conjugated alkenes. Let's look at the orbitals of this thing. We're going to, just as we did with the conjugated pi systems, the acyclic conjugated pi systems, we're going to only consider the p's, pi's, and pi stars. Because in Huckel molecular orbital theory, we just look at those. We ignore the sigma bonds. Because these guys are the ones that are interesting. They're the ones that are the frontier orbitals, and also the sigma orbitals are in the nodal plane of the pi system. And therefore, they don't talk. We've got 6 p orbitals. We've got 6 sp2 hybridized carbons. Therefore, we have 6 p orbitals in a ring. And our lowest energy orbital always has the maximum amount of conjugation. So the maximum amount of bonding, in-phase overlap. If we put one node, we should have something there. And if we put one node into this, it's going to have to cut across the whole molecule. But it turns out there's 2 to do that. I could draw a node going this way or at right angles going that way, and those give me 2 different orbitals. Notice that this one has 1, 2, 3, 4 in-phase overlaps and 1, 2 out-of-phase overlaps. And if, bonding and anti-bonding cancel, this has kind of net 2 bonding interactions. This guy also has net 2 bonding interactions, because remember in Huckel theory we mentioned that we only consider adjacent positions interactions, and this position is not adjacent to that position. So these two turn out to be what's called degenerate, and in a chemistry context that means having the identical energies. So we've got 2 ways of making orbitals with one node, and they have identical energies. It turns out our next orbitals have 2 nodes, and I can either cut 2 nodes by making slices across the molecule this way and this way, or this way and this way, and in each of these cases I'll get new molecular orbitals, which again are degenerate. This one has a net 2 antibonding interactions, as does this, because this has antibonding, antibonding, bonding, antibonding, antibonding, bonding. And this one just has antibonding and antibonding. So again, same energies. If I was to put 3 nodes across this molecule, cutting from here to here, here to here, and here to here, I'll get this guy that's all out of phase. And that's going to be the highest energy combination. Here's a bird's eye view picture. That's basically putting my eyeball above the pi system and looking down. So we're just seeing the top halves of the p orbitals. And this makes it a little easier to see where the nodes go. Here or here for the second and third orbital, and here, here, or here, here for the fourth and fifth. And then the highest energy one has nodes that essentially bisect each of the sides. Huckel is able to go and calculate energies for these and fill in electrons, and we find out that we have 2 orbitals that are tied for being the highest occupied, and 2 orbitals that are tied for being the lowest unoccupied. Let's construct these orbitals a slightly different way. Let's start from hexatriene. These are orbitals that we saw in hexatriene when we looked at the acyclic conjugation. And let's imagine sort of wrapping the ends around to bring them close to each other to make a loop. Now notice this is not how the actual molecule benzene is formed, because I'm totally ignoring all the sigma bonds here. And hexatriene has more hydrogens than benzene. So this is not how the molecule forms. I'm just looking at the loop of p orbitals, because in Huckel theory that's all we consider. Now if I imagine bringing this dark blue orbital, imagine wrapping this molecule around so that the ends come close to each other. For the dark blue orbital, as this carbon comes close to this carbon, that's a bonding interaction, because those would be in phase. And as I bring the ends closer and closer to each other, the energy of this orbital will be going down. For this guy, the next one up that I've shown in red, as I bring this end close to this end, that's going to be an out-of-phase interaction. So as I bring the 2 ends closer to each other, the energy of this guy is going to go up. This guy, as I bring the ends closer and closer together, the energy is going to go down. Notice the red and the light blue, or aqua, whatever you want to call that, are getting closer to each other. Same thing with the purple and whatever color that is, goldenrod. And this one's going up. Eventually we get those orbitals that I just showed you for benzene, where we've fully made the loops, and these 2 are degenerate, and these 2 are degenerate. Now we had previously given energies in the acyclic conjugation chapter for hexatriene, and here's the pi energies here's the orbital energies for benzene and their orbital occupancy. Let's calculate the pi energy. We already know from when we talked about conjugated systems that we can calculate the pi energy by just considering the energy of all of the electrons in the pi system. So for hexatriene, I've got 2 electrons at this energy level, 2 electrons at this energy level, and 2 electrons at this energy level. And the total of that is 6 alpha plus 7 beta. For benzene, well, I've got 4 electrons at this energy level and 2 electrons at this energy level, and I get 6 alpha plus 8 beta. Notice that for benzene, we get overall a more stable system because we've got cyclic conjugation as opposed to the acyclic conjugated system. So it seems like we're getting some extra stability from that cyclic conjugation. That extra stability is called aromaticity. Benzene and structures like benzene are classed as aromatic compounds because they've got this resonance stabilized conjugated system where you get special stability due to the cyclic conjugation. But we got a problem, and that problem is cyclobutadiene. Because we just said that a series of alternating single and double bonds in a ring that has resonance gets this extra stability. So we should predict that cyclobutadiene should also be very stable. Draw resonance here, and you can imagine a delocalized system that should be very stable if the previous argument holds fast for this. But it turns out this isn't stable. This is actually very unstable. And all of those things that we said about benzene that were interesting about benzene turn out to be not true about cyclobutadiene. We said that benzene was delocalized and that all the bonds were the length. It turns out this one is actually not. It's actually rectangular. And there's actually, instead of a resonance, there's an equilibrium between the two rectangles. We said that benzene was particularly stable, and this turns out to be very unstable. We said that benzene does not react is less reactive than alkenes and reacts differently. Cyclobutadiene does addition reactions just like alkenes, and in fact it's not less reactive, it's much more reactive than just normal acyclic alkenes. Now you might say, well, this is just a four-membered ring and four-membered rings are strained. But it turns out this isn't just about the four-membered ring. This is also about the pi system. Remember, the Huckel theory is just about the pi orbitals, and the strain should be about the sigma bonds, because the angle strain involved in a square is all about the sigma interactions. So what's going on here with cyclobutadiene? Why is it so unstable? Yeah, there's strain, but we'll see that it's not just cyclobutadiene. Strain is going to be, lots of pi systems are going to be particularly unstable, whether or not there is strained rings. Well, let's consider the orbitals. If we've got 4 sp2 hybridized carbons, we should have 4 p orbitals, and therefore we should have 4 pi combinations. Just as before, the lowest energy combination will have all in-phase interactions, and then we can have one node either this way or this way, or 2 nodes here and here. Here's bird's eye view pictures of the same thing. This one has 4 bonding interactions. These each have 2 bonding and 2 anti-bonding, and so therefore net nothing, net 0. And this one has 4 anti-bonding. And Huckel calculates the energies of these orbitals as alpha plus 2 beta, alpha, and alpha minus 2 beta. And again, these two are degenerate. If I've got 4 electrons within these 4 pi orbitals, we start filling in from the bottom up. 1, 2, 3, 4. This is our orbital occupancy. Interestingly, this guy is like a diradical. It's got 2 unpaired electrons. That might be a clue as to its reactivity. But let's go a little bit further. Let's compare butadiene to cyclobutadiene. If we took the orbitals of the pi orbitals of butadiene and imagined bringing the ends closer to each other, of course, if I bring these 2 ends closer to each other, that's an in-phase interaction, so I'm going to get something more stable. If I bring these 2 together, I'm going to get something less stable. These 2, I'm going to get something more stable, and these 2, I'm going to get something less stable, until eventually I get to the fully cyclic molecule. Notice that the green and dark blue orbitals have converged in terms of their energies. So here's the orbital energies of butadiene and cyclobutadiene, as we've seen before when we talked about conjugated systems, and here the orbital energies I just gave you. let's calculate the pi energy of these two. For some reason I didn't write it down on this slide, but this butadiene is going to give us an overall energy of 4 alpha plus, sorry, I should have done this before, 4.44 beta. Cyclobutadiene, the total pi energy is going to be 2 electrons at this energy level and 2 electrons at this energy level, which is 4 alpha plus 4 beta. The acyclic species is more stable than the cyclic species. Now this is in contrast to what we saw with benzene. In benzene we saw that the cyclic was more stable and we called that aromatic. In this case, see that the cyclic thing is less stable, and that's going to be called anti-aromaticity. So now we've got two types of pi systems, some of which seem to be more stable than acyclic conjugated systems, and those are called aromatic, and some that are less stable, those are called anti-aromatic. So how can we predict which for a given pi system, whether it will be aromatic, that is particularly stable, or anti-aromatic, that is particularly unstable? Well, Huckel came up with a rule. He said, well, let's look at things that have a conjugated loop of p orbitals. That is a ring where on every position we've got a p orbital. And if you look at that ring, if you count the number of electrons within the pi system, defined by those p orbitals, if you have 2, 6, 10, following the pattern 14, 18, 22, etc. electrons. And that's sometimes abbreviated as 4n plus 2. If n is an integer, 4 times 0 plus 2 is 2. 4 times 1 plus 2 is 6. 4 times 2 plus 2 is 10, etc. Well, those things are called aromatic. That is, they are particularly stable relative to acyclic systems. On the other hand, systems that have a loop of p orbitals with 4, 8, 12, 16, that is some multiple of 4 electrons, those are anti-aromatic. Those are things that are particularly unstable. So this isn't about strain. It's not about the fact that 6-membered rings are good sterically or in terms of angle strain or whatever. It's all about the number of electrons within that loop of p orbitals. So let's look at these 4 molecules on the bottom. First one, I'm sorry, before I do that, I have to say, if things don't have a cyclic conjugated loop of p orbitals, they're non-aromatic. So things are either aromatic, anti-aromatic, or non-aromatic. So let's look at these 4 molecules along the bottom. The first one is non-aromatic because it's not a loop, right? It's not a ring. So the aromaticity and anti-aromaticity don't apply. The second one, well, here we have a ring, and if you look around the outside of the system, there's a continuous ring of sp2 hybridized carbons. So there's a p orbital here, 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 here. You could count around the outside. And within that ring, there are a total of 10 electrons. That fits the aromatic pattern. And this is naphthalene, and naphthalene is particularly stable. It's like benzene. This third molecule, well, here we've got a loop of p orbitals, but I've got a total of 2, 4, 6, 8 electrons within those pi orbitals. And that's an anti-aromatic pattern. That is, cyclooctatetraene turns out to be particularly unstable. And then this fourth molecule, cyclobutadiene, it's a loop, but there's not a p orbital on each position because this carbon is not sp2 hybridized, it's sp3 hybridized. So this molecule is non-aromatic. Now, this doesn't only apply to neutral hydrocarbons. We could, for instance, look at charged species. So here are 2 cyclic carbocations, each of which is a loop of p orbitals. Because remember, a carbocation is an sp2 hybridized carbon with an empty p orbital. So the molecule on the left, cyclopentadienyl cation, has, well, it's got 2 pi bonds and an empty orbital, the carbocation. So that's a total of 4 electrons in the pi system. On the other hand, the molecule on the right, it's got a loop of p orbitals with 3 double bonds and a carbocation. So that's 2, 4, 6 electrons. It turns out the molecule on the left is particularly unstable. It's anti-aromatic. The molecule on the right is particularly stable. It's aromatic. It's, by the way, has the trivial name, the tropylium ion. Generally speaking, if something has a trivial name, it's probably a stable molecule. All right. My daughter thinks that's funny. Okay, we could also look at carbanions. So if we assume sp2 hybridization, which is a little bit of an assumption, but let's just treat it for now as if all these carbons are sp2 hybridized, we would have a loop of p orbitals. But in those loops of p orbitals, we've got some that are involved in double bonds, so 2 electrons shared between 2 p orbitals. And then if I have an sp2 hybridized carbanion, there's a pair of electrons within that p orbital, because the sp2 hybrid orbitals are involved in either the carbon-carbon or carbon-hydrogen sigma bonds. So in this case, the cyclopentadienyl anion, the one on the left, has 2 or 6 electrons. On the other hand, the cycloheptatrienyl anion on the right has 2, 4, 6, 8, if you count 2 for each double bond and 2 for the lone pair. And therefore the molecule on the left is particularly stable. That is, it's aromatic. And the molecule on the right is particularly unstable. That is, it's anti-aromatic. And we're not even limited to hydrocarbons. We could also have heterocyclic molecules. To an organic chemist, a heteroatom is something that's not carbon or hydrogen. And usually we're talking about things like nitrogen or oxygen when we talk about heteroatoms in organic chemistry. So here's some rings that have nitrogens and oxygens, and notice that they've got lone pairs. But the real question is that lone pair part of the pi system or not? Let's look at this as loops of p orbitals. If these are planar rings with sp2 hybridization at each position, the nitrogen and oxygen, the nitrogens and oxygen would each be sp2 hybridized. But what would those orbitals be involved in? Let's take the first molecule. The sp2 hybrid orbitals in the molecule on the left are involved in carbon-carbon and nitrogen-carbon and nitrogen-hydrogen sigma bonds. And then there's a p orbital, and the lone pair must be in that p orbital. So the molecule on the left turns out to be, well, it's got 2 electrons for one double bond, 2 electrons for the other, and 2 electrons for the nitrogen lone pair, and therefore 6 electrons, and that's aromatic. The central molecule, this is furan, by the way. The one on the left is pyrrole. The one in the middle is furan. It's got a ring with an oxygen. And now if that oxygen is sp2 hybridized, it's got 3 sp2 orbitals and a p orbital. The 3 sp2 orbitals, well, 2 of them are involved in oxygen-carbon sigma bonds, but then we've got an sp2 orbital and a p orbital. One lone pair is in the sp2 orbital and one lone pair is in the p orbital. So what would Huckel say? Which electrons count? The Huckel rule only considers the loop of p orbitals. And there's a total of 6 electrons in the loop of p orbitals. And so furan is indeed aromatic. And now let's take pyridine, the molecule on the right. Nitrogen is, if it's sp2 hybridized, which it is, well, it's got 3 sp2 orbitals and a p orbital. But notice nitrogen has a double bond to carbon, and therefore the double bond must be an overlap of p orbitals. So notice these 2 electrons are shared in a pi bond. This lone pair here can't be in the p orbital. It's got to be in the sp2 orbital. And so that lone pair doesn't count as far as the Huckel rule goes. And so pyridine has 2, 4, 6 electrons in the pi system, the loop of p orbitals. Therefore, pyridine's actually a lot like benzene as far as the pi system goes, and it's aromatic. Now, this idea of aromaticity and anti-aromaticity and non-aromaticity helps explain a lot of things. Let's look at a couple of examples. Here I show two molecules, cyclobutadiene and cycloheptatriene, and they have very different pKa's. Recall that pKa is a logarithmic scale, and so if I have two things that are 20 pKa units different, this guy on the left, cyclobutadiene, is 10 to the 20th times more acidic than the one on the left, the one on the right. This one, the lower pKa, is the more acidic. Now, pKa of 16, that's like an alcohol. That's not like a hydrocarbon. Alkanes have pKa's, around 60-ish. Alkenes, I don't know, 40, 50-ish. Alkynes, terminal alkynes, which we said are doable, they have pKa's still around 20-something, 22 or so, 24, depending on the alkyne. But this is like an alcohol. You say, okay, why is this so acidic? Well, what does acid mean? Remember, what it means is that you pull off a proton and you get the conjugate base. And so if we take the cyclopentadienyl and we pull off a proton, we make the cyclopentadienyl anion. If we take cycloheptatriene and we pull off a proton, we make the cycloheptatrienyl anion. And, you might look at these and say, well, they're both resonance stabilized, but that's not actually true. We can draw resonance forms for both, but the top one, the cyclopentadienyl anion, is aromatic. The cycloheptatrienyl anion is anti-aromatic. And so in the top case, deprotonating cyclopentadiene leads to something that's particularly stable. Deprotonating cycloheptatriene leads to something that's particularly unstable. And that's the source of the fact that this is so much more acidic than this. That is 10 to the 20th power times more acidic, easier to remove a proton than this one. Or let's take another example. If I take chlorocyclopentadiene and chlorocycloheptatriene and treat them each with water, the first undergoes no reaction and the second undergoes reaction. Now, if you look at this, this is some sort of substitution, right? We're replacing a chlorine with an OH. But this is a weak nucleophile, so this is an SN1 substitution, right? That's the mechanism that we're considering here. But how does a mechanism for SN1 work? Well, it starts out by losing a leaving group to make a carbocation. Now, in the first case, if we were to lose a leaving group to make a carbocation, we would make something that was anti-aromatic. On the other hand, in the second case, we would make something that is aromatic. And so that's reasonable to do. So it's so you're not going to do this first process. No reaction will occur. In this process, this will leave relatively readily to make a reasonable carbocation, and then water comes along, and after loss of a proton, we get this alcohol as our SN1 product. Let's just wrap up a few other things about aromatics before we talk about the reactions of them, which will be our next unit. Naming arenes, there are a lot of trivial names. Just reading from left to right on this slide, the top one is naphthalene, and in fact there's names for things with 3, 4, 5 benzene rings in a row. When there's groups attached to a benzene ring, a lot of those have trivial names, like methylbenzene is better known as toluene, hydroxybenzene is better known as phenol, methoxybenzene is usually called anisole, aniline benzoic acid. When there are more than one substituent on a benzene ring, there are special names for the substitution patterns. We could just number them. IUPAC numbering works. We can say that the first molecule here is 1,2-dichlorobenzene, 1,3-dichlorobenzene, and 1,4-dichlorobenzene, respectively. These are generally called ortho, meta, and para. So when you've got two substituents on an aromatic ring, on a benzene ring, you generally refer to them by these ortho, meta, or para, or just the abbreviations O, M, and P designations. The heteroaromatics are also, there's a lot of trivial names. Some of these I mentioned previously. Pyridine, that's not spelled right. It's pyridine, Pyridine. Pyrrole, furan, benzofuran. Another naming thing is if benzene is a branch off of something else, it's called a phenyl group. So in this case here, on the left, this guy would be named as phenyl cyclohexane, because here I've got a cyclohexane, and it's got a branch, and that branch is a phenyl. Phenyl is sometimes abbreviated as a pH, as a, well, technically as a phi. I just didn't like the font that phi came up with. So sometimes you'll see that. An aromatic ring is sometimes, you know how we've used before R to represent some carbon group. AR is used to sometimes represent some aromatic ring attached up here. And another just drawing thing that's worth mentioning is sometimes people will draw a benzene ring. Instead of having alternating single and double bonds, they'll draw a hexagon with a circle inscribed. And that's to represent the fact that there's a delocalized set of electrons in such a ring. Oh, I should have mentioned that an aromatic ring as a branch is sometimes called an aryl group. So that's a generic term for any aromatic ring. If it's specifically benzene, that's a phenyl group. One last thing I want to mention here is phenol. That's hydroxybenzene. If you look at this, it's technically an enol. If we just focus in on this portion, there's an ene, here's an alcohol. And we've always said in the past that whenever you see an enol, it will be transformed to the keto, and there's this equilibrium, right? And for most things, this equilibrium favors the keto form. But in this case, the equilibrium favors the enol form. Because why? Huckel says that this guy over here is non-aromatic, and this guy is aromatic. And that's why. So it's going to look like this, because that's a much more stable arrangement than that. Or it's going to be like this 99.9% of the time, because in the equilibrium, that is much more stable. Phenol is particularly acidic. Most alcohols have a pK of around 16 or 17. Phenol has a pK of around 10. So this is much more acidic than other alcohols. Why? Because the conjugate base is stabilized by resonance. I could draw out the resonance forms and put a minus on this oxygen, but I could also share that across the ring. All right. That's pretty much it. So we are going to go on and now in our next section talk about the reactions of aromatic rings. All right. See you then.